Very good. And we are here for the second hour here on June 24th, Wednesday. This is part 4 of chapter 16. Remember, homework 1 is due tonight. You need to write it out by hand and scan that and upload that. If we got time here, we'll work a couple of these problems, but you can get help in recitation also, or send us emails or whatever. You should have access also to the solution manual. You had that before in 351. Of course, it continues here in 352. If you just got the book now, you need to go to the bookstore, and I'm not sure how we're going to handle that. If you're new to BYU and just getting the book now, we need to see how we can get you that, the solution manual. And also, we have the help room, W151. We're handling it electronically. Colin is helping us out in there. He's the TA for that. And I need to put his contact info on Learning Suite. You'll see that. Maybe I'll send out an email on that. And of course, Thursday is also something due. What quiz 1? And you need to print that out or get a hold of that PDF on Learning Suite under Content. There's a tab for quizzes, and do that by hand. Enter all your answers there, and then snap a picture and upload that by Thursday. Okay. And what do we have up here? Looking up here on the overhead, we have CHEM352 3D. Yes, we have YouTube and we have CHEM352. And this is this free animation 3D, completely interactive program offered through the University of Liverpool in the UK. And it's a great resource for beginning chemistry students, including organic, of course. And if you had me for 351, I've shown you a few of these. What we have here is Diels-Alder reaction that's being animated here. We have Cyclopentadiene reacting with maleic anhydride as the dienophile and forming the Diels-Alder product. And this is a kind of a complicated one now. We're going to get into these examples today. But you can access these. So you get a hold of the Diels-Alder reactions right there, the pull-down menu, and there's a whole bunch of options to look at. So it's a great thing. And you need to click on the arrow then to activate the 3D animations here. Then you have controls over it. You can play backwards and forwards. These are concerted reactions. This Diels-Alder reaction, just exchanging the pi bonds and the sigma bonds. It lets you rotate it around here. I'm holding it with my mouse right now to change the orientation there, but I have the button here to play backwards and forwards. So you can see the transition state over and over again. And this is great for the harder type of Diels-Alder reactions, especially the Endo rule ones that we're going to get into today. So let's come over to the board here and start to work some of these problems. We've got some of the simpler Diels-Alder reactions that we've got right here, and we're going to look at these. We had butadiene last time, and I think we had an aldehyde up here, but now we've got an unsaturated ester, you see. Then we have this maleic anhydride again. Then we have a quinone here. We have a couple different dienes. So you can see the versatility of the Diels-Alder reaction. You need to, though, just focus on the main part, which is the diene and the dienophile, and then just push the electrons around the ring, okay, and get the cyclohexene product. Make sure you put everything that was on the diene and on the dienophile in the proper location. So that would be the product there. You can focus on the cyclohexene part. Remember, this is the transition state. It's a concerted reaction. It happens all at once when those pi systems collide. It's in the pericyclic class of compounds. It's technically called a 4+2 cycloaddition. We'll call it a Diels-Alder reaction. That's okay. It's the most common type of cycloaddition, with 4 carbons involved in the diene, 2 carbons involved in the dienophile, hence a 4+2 cycloaddition. But focusing on the key product here, the cyclohexene product, and then whatever else was on there goes along for the ride. So let's do the same thing here for this reaction. So we've got a methyl group here now on isoprene and the maleic anhydride. And let's draw the product here. We still have the anhydride part. We have the cyclohexene. Is that it? No, there's a couple things we need to add here. We got this methyl group. Where did that end up? Well, it's right here, okay? Remember, we just formed that bond, and we moved this pi bond over. Is that fully correct? Is there one other thing we need to address? Ah, that's right. What about these two hydrogens here, okay? You see they're cis here in the starting material, and they need to wind up being cis to each other in the product. And we'll examine the transition states carefully, and you'll see why that's so. When it collides together, the stereochemistry here of the starting materials is maintained there. So those two hydrogens there will end up cis. Make sure you define those at that position. Okay, what about this one? We've got butadiene with a couple methyl groups here and quinone. So let's go ahead and react there. Don't worry about the one on this side. If we had excess of this diene, you could get another Diels-Alder reaction over there. But we'll just look at the one where it's 1-to-1 equivalency here. So what's our product? Cyclohexene, always the product of Diels-Alder. Now we just have to add everything else. So, you know, if you're doing a Diels-Alder, you can almost always just draw the cyclohexene to help yourself out there. And then the rest of the quinone, which ends up that. So we could use that as another Diels-Alder dienophile over here. Is this done? No, we've got the two methyls. Make sure you draw those in the correct spot, there and there. Not here or here, okay? Those spots are methylenes, CH2s. And you see their methylenes right here. Ah, what about these two hydrogens that are right here? We don't always draw hydrogens, but you gotta keep track of them in the Diels-Alder action. That's right, they're cis, so they'll be cis in the product. Now, let's examine the Diels-Alder a little more carefully. Yeah, we have the new sigma bonds and everything here, and the pi bond moved over there. What about the hybridization changes here? We've got sp2 hybridized for everything that's reacting here, right? So there's a rehybridization in the product to make these sigma bonds now. These carbons right here are what? They're not sp2 anymore. What are they? That's right, they're sp3. Okay, so it underwent a rehybridization process, and our transition state will hopefully bear that out, and we can see that though. Let's do a couple other simpler ones. Most of the ones we'd have on a quiz or a test are going to be these simple type of Diels-Alder reactions. The Endo rule and handling the stereochemistry with more complex examples. We'll get into that here in a minute, and by being able to analyze the transition state, we'll help ourselves out with that. So let's see, how about another one here? How about a methyl ketone? Oh, and how about a vinyl nitro group? Okay, and we may want to analyze this from an electronics point of view. So let's see. Let's examine this. So what do we have here for the resonance structure for these? Well, we can push the electrons up toward what's called the electron withdrawing group, okay? Which means we can polarize these electrons in this way to create what? An electron deficient dienophile. In fact, that's the hallmark of why this works. Remember, we said ethylene on its own, just unsubstituted, simple ethylene, is a very bad dienophile. It just won't react, okay? But if we have an electron withdrawing group, that actually electronically matches this here. And you can see now, we can push the electrons here, and we can actually stop at this point. Let's go ahead and put our diene on there. And what would that look like? Well, we'd have this, right? We'd have this type of an arrangement, okay? And that's just going part way through the Diels-Alder reaction. Sorry to keep changing stuff up, but make sure your notes are clear on this. So this is kind of a stepwise, idealized transition state for the Diels-Alder reaction. It's not happening this way, but electronically you can see why the withdrawing group might be important. Let's just attack here and push the electrons up here, We get this intermediate. Well, that doesn't look like our cyclohexene yet. But let's bring a pair of electrons back down here, make that second sigma bond, and push these electrons over here. So what is the product here? It's cyclohexene again. Methyl ketone is still there. And yeah, it's the same thing, right? If we just did this together at the same time, like we've been doing. But you can see how this withdrawing group helps make this electron deficient. This is electron rich, and electronically that allows for these type of Diels-Alder reactions to go at lower temperatures. Sometimes we draw a delta here for the Diels-Alder reaction. If you need to warm it up, delta means heat or warming. And sometimes we have to elevate the temperature a little bit to get them to go. The ones with the 2 carbonyls conjugated, those actually go at room temperature or lower. So some of these I'm showing you here are very good. Vinyl nitro is very good too. Let's draw out the nitro functional group, and you can kind of see what it is, right? There's the formal charges there. You can see the positive charge. We can begin to pull these up here as we react this with that. And let's just go ahead and do the whole thing. And so we'll have cyclohexene with a nitro group on there, okay? It's a very good way to make the nitro cyclohexene. But you can see electronically that's going to be pulling electrons out of there to favor that. All right, let's look at our transition states for this reaction. And we're going to go to a different diene. Let's go to cyclopentadiene. We only need to modify things a little bit here. We're going to put a methylene right here. And yeah, let's do it. Let's go back to our aldehyde. Okay. See if you can come up with a product for that. Diene, dienophile, right there. What is the product? Oops. Okay, well, maybe we need to warm it up a little bit. What's that product? If you want to pause the video right there, you can. Okay, and now we're back, and let's see what product you got. So you can always just draw the cyclohexene, right? And what else is on there? The aldehyde. But what else is on there now with cyclopentadiene? Yeah, this methylene. Where does that go? Look, it's right here. It's right in between these 2 carbons. So that would be the product right there, okay? So it's got this bridged bicyclic system there. You see a 5-member ring right here. This is from the cyclopentadiene. And this is the complexity of the Diels-Alder reaction. Moving forward, it's not much of a change, just an extra methylene. But look at the product now. You can see the cyclohexene embedded here. But you see a 5-member ring here. And do you see another ring right here? Yeah, there's another 5-membered ring right here. And the aldehyde. Let's look at this in 3 dimensions. Let's tip this on its side and see what it's going to look like. Okay? It's going to look like this. Okay? This is just reorienting this, tipping it up, or however. Maybe my arrow should be kind of like that. About 50 degrees or so, okay? And we'll get a model here in a second where you can see this. But you can see the cyclohexene right here, the 6-membered ring. There's our alkene now in the back there. You see this methylene right here, which is right there. 2 hydrogens on the side coming out right here and here. Hydrogen right there and a methylene right there. And there's our aldehyde, of course. Now, the question is that. We drew it that way. Let's see. How is the transition state? Because we could have drawn it like this, right? Could have had the aldehyde coming up like this. These are isomers of each other, right? Here I kept these 2 stereocenters the same. We kept this stereocenter not the same, right? We inverted it relative to that. And this hydrogen is here, right? Here it's up right there. You can see the difference between those 2. What's the transition state look like for this? Let's tip this whole thing kind of on its side. Yeah, you need to be able to do this, and with the models here in a second, hopefully you'll see it a little more clearly. And here's the pi systems, right? The p atomic orbitals kind of helps to see those in dimensions, right? And then we've got the dienophyl here, right? And we can either have the aldehyde down underneath here, and we're going to call that the endo position. And we'll redraw the transition state for the exo here in a second. But let's go ahead and do the reaction. So we're going to react here, here, and then this, you see, will become the double bond back there. So this is where our sigma bonds are going to form. And this is where the new pi bond is going to be there. So we're just reorganizing, right, the pi bonds of this. Let's draw this product here with the same orientation. And what we get is the aldehyde down underneath here and the alkene right there. Everybody see how this, touching those pi systems together now, makes these two bonds right there and there, okay? And because we've got the aldehyde tucked underneath here, this hydrogen's coming out right there, okay? And notice this hydrogen here is cis, or on the same face of these pi systems as the methylene right there, okay? And so when you flatten this thing out, what is this? It's the same as this drawing right there, okay? So let's look at the models here and see if we can come up with that. So here we've got cyclopentadiene. You see the blue pi bonds there, and there's the black for the methylene. That's showing up okay. And that here's our dienophyl, and there's our aldehyde. Here, let me put the aldehyde there. Okay, the aldehyde's this red thing. Okay, and then here's our where I'm holding my hands is where the sigma bonds are forming. Okay, you see that? Maybe. Okay, maybe over there a little better. Okay, it's kind of molecular magic or wrestling here, right? But you see the cyclopentadiene, which is up there, that's our diene. Where my hands are, the new sigma bonds, right? And then the new pi bonds in the back there. You see, those are going to overlap now. And then what? You see the hydrogen sticking up right here on the aldehyde next to my right hand there. This would be the hydrogen. Sorry, everything's flopping around. But yeah, tucked underneath there. And then we go to this model right here. You can see that structure, that bridge bicyclic structure with the aldehyde pointed down. And we call that the endo transition state. This is always the favored one for any Diels-Alder transition state. And why is that? That's kind of a strange thing because this aldehyde is tucked underneath there. We could have the aldehyde out here, which would lead to that exo product, the other one we're going to draw here in a second. We'll analyze that transition state also. But this is the favored one. And it has to do with a couple things. One, there's an extra pi bond here on the withdrawing group that can get some beneficial overlap. It's called secondary orbital overlap with the diene. And you only get that in the endo transition state. Now, a lot of times in the simple Diels-Alder reactions, you can't tell whether it's endo or exo, okay? It's only when you have two stereocenters here being formed right next to each other, you need to worry about it. So with cyclopentadiene, we have the methylene and this hydrogen here that's going to form a stereocenter, you see right there and there. So now we need to worry about whether this is endo or exo. If you just draw this here, you don't define the stereochemistry. We need to draw it with some stereochemistry here. So this needs to be up like that, okay? And this hydrogen needs to be up. Or we can draw this, okay? Either one. Either one of these depictions is okay. This is the flat view looking up at the top here of this one. And here you actually see the relationship between that hydrogen and that methylene. being the endo product. Okay, let's analyze for the exo product here. I'll push up the board, but we'll still be able to see this bottom part. So let's get a new view here, and we'll look at this arrangement leading to the exo product. So we have our same pi systems here. Let's have our aldehyde out here now. So there's our pi bonds interacting with each other. Let's get them all on there. And you can see they're already touching there. So we're gonna, bring our electrons here, and over here. And we're gonna get our product. And let's keep things oriented the same here. You see our aldehyde's gonna be out here. There's our new pi bond back there. And where is this hydrogen? This hydrogen, you see, is back underneath here. It's in the endo position, actually. This is the exo position. There's no secondary orbital overlap between the withdrawing group and the diene. You see, in the endo transition state, the aldehyde's tucked underneath. That's a very subtle effect. It's a complicated effect, but it has different stereochemical outcomes here. See, this hydrogen is down right there. So we can redraw the product, and we can make sure we've got the exo product. Okay. Now that's a little bit tricky, okay? But the one that's favored is the endo product. They're actually diastereomeric to each other. They're both chiral. They're both formed in racemic form because we could do the enantiomeric thing, the endo just twisted over to the other side, which would give the enantiomer of this endo product. Or we could, you see, have the aldehyde over here, and that would give the enantiomer of this, okay? But it's the relative position of the withdrawing group to whatever is on the inside of the diene right there, okay? So there's the hydrogen coming down. And again, let's look at the models. And now for the exo. Oh, get the right view there. Okay, so here's our aldehyde. It's the red ball, right? And you see it's out from underneath the bottom of the diene, right? So it's creating a different stereochemical relationship between this aldehyde and what becomes the methylene here bridging the bicyclic system. There it is right there. By the way, this type of structure has a name. It's norbornane. Well, it's got an alkene, so we're going to call it norbornene. It's actually common in a lot of terpene compounds in plants. A lot of essential oil compounds have this norbornane type bicyclic structure. So we can make all of those using different variations of the Diels-Alder reaction. So this endo-exo thing is a little bit tricky. We can apply it for even the simpler systems, but again, you don't see the stereochemical relationship unless you're creating two stereocenters within the molecule. Then you need to see the relative relationship between them. All right, let's work a couple more problems here and see if we can get a handle on some of these trickier problems. And I'll do the transition state analysis for each one. So let's see. How about this variation? Let's have, back to the simple one, butadiene, plus this unsaturated carboxylic acid. So this is a phenyl group of benzene over here, a trans or E double bond right there, and then a carboxylic acid. Now this has a carbonyl that's conjugated to the dienophile, right? So that's going to make this reaction go quite well. Let's push our electrons around the ring. And yeah, cyclohexene. That's what we're forming. And there's nothing else on the butadiene. That's the easy part. I'm showing this example because of these two groups. We've got the phenyl and we've got the carboxylic acid. What's the relationship between those two? Well, it starts out E, so what do you think here in the product? Are they going to be cis or trans to each other? right? They're going to be trans to each other, okay? So for full credit, you need to show the relative stereochemistry. That's indeed a chiral product. We can form the enantiomer of that also with the enantiomeric transition state I'm going to show you. But I'll show you the transition state that leads to that isomeric form. So let's look at the butadiene kind of sideways there, tipping it up. And we've got the dienophile here. And we're going to have the carboxylic acid, you see underneath in the endo position. So there's our pi systems touching there. You don't need to draw that out each time. But what you see is this hydrogen here and this hydrogen back there, right? This is trans, the benzene and the carboxylic acid. So let's go ahead and form the product here. And let's see. So our double bond there. There's our carboxylic acid down there. Hydrogen coming out right there. Okay, hydrogen, carboxylic acid. And relative stereochemistry, again, 2 stereocenters. So we need to define the endo rule here and keep track of this. And there's the other one going back. And so there you see it's the same as that. That phenyl is up and the carboxylic acid is down there. So that's the endo rule applied to that one. Now, you could solve this problem here without invoking the endo rule and the transition state and just recognize these are trans to each other, and that would be fine. It's really when you have something on the diene here, and then something on the dienophile, like with the one we just did before. But that's a good example to go through and invoke the transition state. So if we had the cis form of this, we could go through the same thing, right? With butadiene and cis form. And what would it form here? Same product, except with what? Cis stereochemistry here, right? So the Z, olefin, alkene, dienophile, would go to the cis Diels-Alder product there. Okay, very good. Let's see a couple more examples. And, yeah, I think we got time to do a couple of the trickier ones now. Let's see. Let's see how we can handle this one. Well, we'll do a couple. So let's see. How about back to cyclopentadiene with the unsaturated ester. Oh, and let's put an extra methyl group there. Let's see about that one. How about cyclohexadiene? Oh, make it a little more complicated. And let's do that with, let's see. Oh, how about, let's do it with the maleic anhydride. Yeah, okay. Now, if you want to pause here, and then click on here in a second after you try these. And we're back, and let's try these. So your product here would again be this norbornene product. There's your cyclohexene there. Sorry about, when you have a bond in front of another bond, you kind of have a blank space there. So that's, I draw the norbornene. And then let's see, we're going to put our ester down here. Okay, that's actually in the endo spot. And we're going to have this methyl group up right there. Okay. Now, if you draw that in a flat view, what would it look like? It would look like this, where you'd have the ester down and the methyl group up. And you see the ester, the methyl ester is tucked underneath there. And that's part of the endo rule. And you can draw the transition state for it. Let's see, you'd have this, and you'd have the ester down underneath here. You have the methyl group there, and then you go ahead and react these pi bonds. And what? You get this product where, yeah, you've got the ester down underneath, and the methyl group would be up right there. Sometimes it's better to focus on the hydrogens that are on the dienophile. You see your hydrogen here is up, and your hydrogen here is down relative to the methylene. Okay, so that, for full credit, is a tricky one. This I consider a hard Diels-Alder problem because you have the endo effect and you have the stereochemistry on the diene. Most of them will be the relatively simple ones where you don't even need to worry about the endo rule, but you can analyze it and figure it out, right? Let's look at this one here with a little bit different diene. It's already got a cyclohexane, right? That can be confusing. Now we'll have an ethylene bridge going along. With this one, we had a methylene bridge, but you know, what's going to be the product? Go ahead and just do the simple mechanism here and draw the product. You're going to have this. Okay, there's your original 6-membered ring right there. And then you've got what's left on the anhydride right here. But what do we got to consider? The relative stereochemistry, right? Relative to the bridge, the ethylene, and the anhydride part. So we need to invoke the endo rule and draw that. The endo rule always dominates. Sometimes it's not so much. Usually it's about 10-to-1 selectivity of endo over exo. Secondary orbital overlap is just one argument. It's actually more accurate to look at the volume of solvation and the interaction of the solvent. The endo transition state is considered to be a tighter, more compact volume of activation. It takes up less space in the solvent. The exo product is more elongated and requires more solvent organization. It's actually an entropy effect to dominate the endo product over the exo. But for the purposes of our class, we'll just stick with the secondary orbital overlap. That's the one in your book. Okay. And we can see that with these activating groups tucked underneath the diene. And that's what we need to do now for this. So let's draw our diene here. And then we'll have our dienophile underneath here. And we've got to have, it's a little bit hard to draw sometimes. Okay, there's our pi systems coming together. And I'm not going to draw out all the pi bonds again, but see these hydrogens here and here, and you can see the carbonyls here are underneath where the diene is, okay? So I know it's kind of a messy drawing, and I don't get any extra credit for being a lousy artist. Okay, maybe you will when you have to write it out. But yeah, sorry the tests are all multiple choice now. But yeah, you need to write things on quizzes still, so you need to practice drawing these things out. But here's the business end, right? Right there to there to there to there, and that's going to be our new cyclohexene. There it is right there. Focus on that. That's the key thing we're forming in Diels-Alder reaction. So can we figure out the stereochemistry here? Let's redraw it. And we've got the product here. We've got our ethylene bridge now there. And where is the rest of the thing? Well, it's the anhydride tucked underneath here. And there it is. Yep, there's our other carbonyl coming up there, right there. And there's those 2 hydrogens. Now you kind of pull it out, and let's see. What will it be? Well, this, let me just modify. Let me redraw. Okay, redraw this. So what would it look like? You got the cyclohexene part, and then you've got the original part there, and then the anhydride. Yeah, a lot of lines going around here. Let's draw some stereochemistry here of this coming up, right? That's this part coming up right there. And then these hydrogens here are also coming up right there and there. Okay. So that would be full credit for the product. Draw these bold, bold, and bold here, or both down if you want it. That would be the enantiomer of this. But that, again, I consider to be a tricky problem. Now let's go to one that I consider to be very tricky. And that's this one here with a couple methyl groups on the butadiene. And let's see if you can work on it for a second and then figure it out. I don't know, it's not too hard. If you can examine the transition state, you can figure out it's going to need to go through the endo transition state. There's going to be some relative stereochemistry here. This will become a stereocenter, right? It's symmetric. It doesn't matter which end you put on there. There's two methyls there. They're both what? They're both E. And that's really the best one conformationally. We can have some conformational flexibility there, and that's kind of a nice review. Let's see. We could have the S trans, right? But this can rotate around to get in the right conformation. It's still EE, right? We didn't change the geometry on the alkene there. It's still EE. But this is the S cis. And that's the one we need in the transition state. If anything can't get into the S cis, I'll show you some dienes that will not work for Diels-Alder reactions. For example, this one. If you have this as a diene, reacted even with the best dienophile, this type of diene, Y, will not undergo Diels-Alder reaction because it's locked in the S trans. You can't rotate around. You'd have to pull this down inside this ring. Conformationally, this cannot do the Diels-Alder reaction. You should be able to verify that. No S cis available here. These two ends have to be close to the two ends of the dienophile in order to get it to go. So anyway, that's a little aside there that kind of reviews the conformation and the requirements of being S cis, okay, which this one certainly can get to. And what's the product? Again, the best way to do this is to start with the simplest part. You're going to form a cyclohexene, okay, and put the other stuff on there. Methyl, methyl, and they're here now. They're at those positions now that are now methine carbons, sp3 saturated carbon. And then the ester, the methyl ester is right here, okay? But we've got stereochemistry here, right? How are we going to analyze that? We have to look at the transition state, right? And that will keep track of the stereochemistry for us. So let's see if we can do that. We've got the ability to look at this. There's our diene. Two hydrogens are kind of poking in toward the middle. And those two hydrogens are in the spot where that methylene was with cyclopentadiene. They were in the inside now. These methyls you see are on the outside. They're E geometry on the alkenes, right? Trans, 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 okay? And let's stick our diene on there. And we need to stick our diene such that we've got the ester underneath. See, our ester carbonyl is close to the diene. That's the endo transition state. And let's go ahead and do the reaction. So what do we get? We're going to get that right there, and that moving over there. That's another way to analyze it. You don't need to draw out the pi bonds each time. But what you see right away is this relative relationship right here and here. And again, like I said, focusing on the hydrogens is sometimes the simpler way to go. But you can kind of see the relationship here between this methyl group now and what? The ester. They're going to end up cis to each other. These two hydrogens you can already see are cis to each other. But let's draw the product and then kind of pull it out and see if we can see the geometry. So yeah, these are the trickiest reactions, I think, geometry-wise. It'll kind of make it tough to see. And what do we have? This hydrogen up right there. And then, yeah, we're kind of moving things around a little bit. You see the two hydrogens here and here, okay? And I've drawn these down relative to looking up at the top here, these two hydrogens up. So those are our two methyls, right? You see? They're on the periphery there. They're in the trans positions here and here. So they end up what? Cis to each other on the cyclohexene. And let's flatten that out. And what do we get here? Well, we get this methyl group down right there, okay? This one also down. And what about this? That's down also, okay? So it's all cis. You can add in the hydrogens there to make sure you can see them relative to each other, but that I consider to be a very challenging Diels-Alder product, okay? Again, most of them on a quiz or a test will be the simpler ones where you don't need to worry so much about the stereochemistry. You can always invoke the endo rule, okay, even with the simpler ones. They do go through the endo transition state, but you just don't see the stereochemistry resulting in the product. But it's good practice to be able to envision the transition states that way. All right, let's do one more here. And this is also kind of a tricky one, which involves some other groups here on the diene. Let's see which one we're going to do here. Let's do this one here. Back to the aldehyde. And instead of two groups symmetrical here, let's put a methyl ether on the diene. Okay, so what's this going to be? So if we draw the Diels-Alder resulting right from that orientation, we've got the aldehyde here and OMe here. Okay, is there another way to do this Diels-Alder reaction? Yeah, it's to flip around the orientations different from each other. Let's have the aldehyde here. Okay, notice the methoxy now is across from the aldehyde. What's that going to look like? Well, look like this. These are definitely what? Isomeric from each other. These are constitutional isomers, right? This has to do with the regioselectivity of the Diels-Alder reaction. And this is a topic that I think is left to one of the harder problems at the end of the chapter. Although they do discuss it a little bit, and I'll show you how to rationalize this. You have to look at the stepwise Diels-Alder reaction. So let's go ahead and do the stepwise reaction here. And if we push the electrons up here, up onto the aldehyde, and just do that motion of electrons, what do we get? We get the carbocation there, our new sigma bond there, and the electrons pushed over, and O minus right there. Oh, we still have the OMe there. Okay. Now, we could just go ahead and finish off the Diels-Alder reaction, push these electrons down, push them over here and get rid of that charge. But we could also invoke what? A resonance form here. And this will control this regioselectivity where you have one electron donating group here, and that's what the lone pair is on that ether, and an electron withdrawing group here. So this makes the complexity a little bit harder. We have to decide which regioisomeric product we're going to form. Let's draw this resonance structure here. What do we get? The double bond moved over. Get the enolate. We've got the OMe. And now you see we have a plus charge on that methyl ether oxygen. And now we can get to the product from here, right? Bring the lone pair down, push it over and up there, and that goes directly to that product. That's only one product, though, where they're what? 1, 2 to each other. They're adjacent to each other. And I'm just using that as a designation. It's not necessarily the naming there. In fact, we don't know how to name those cyclic type of aldehydes, but don't worry about that. They're just together. And here, we could do this. We'd do the same stepwise analysis. And what would we get? We'd get that double bond there, OMe, and what? This, and that right there. Now, can we draw a resonance structure from here? When we have the oxygen here now, and we reacted this alkene directly there. See, here we reacted the end alkene when they're 1, 2 to each other, but if they're 1, 3 to each other, look, we don't have the same resonance structure availability. In fact, this is the more electron-rich end of the diene due to this donation effect of the donor group, okay? It's actually making this carbon also electron-rich, but for the Diels-Alder, we're reacting all 4 carbons here for the Diels-Alder. So this is the electron-rich end. This is the electron-deficient end of the diene. So if we have a donor group here, they prefer to end up 1, 2. If it's 1,3, the orientation, we don't have the extra resonance effect. We can still finish off the Diels-Alder reaction here and get to this 1,3 product. But this one benefits from this extra resonance effect. But what about the stereochemistry here? We've got to figure that out. Let's see. We can handle that easily. Do that quickly here. We've got OMe. We've got a hydrogen up there. We've got this. We've got our aldehyde tucked underneath. There's going to be our Diels-Alder reaction. And so what? You can see the two hydrogens are indeed what? Both poking up there. Here's the electron withdrawing group in the endo position, tucked underneath the diene. And what do we get? We get the orientation here. We've got the OMe back there. The hydrogen in the front. The hydrogen right there next to the aldehyde. But if we bring that up and look at the product, sorry, making you move the camera, you can see the OMe and the aldehyde indeed wind up cis to each other. Okay, and that's due again to the endo effect and also due to this regioselective effect. Now that's a trickier problem, okay? Don't worry, I'm not going to put a bunch of problems like that on the test. Let's show one other example here, and maybe an intramolecular example. The Diels-Alder is a very versatile reaction. You can do reactions with alkyne dienophiles, so something like this, butadiene plus this alkynyl methyl ester, right? See if you can figure that one out. And let's see, just one more here. How about, this one. Got an intramolecular example. That's a great one. Just shows the versatility, I think, of the Diels-Alder. And we're back. If you pause there, let's go ahead and do it. And just push the electrons around. You actually don't need to worry about the endo rule here at all. You just need to worry about putting the methyl ester and the cyclohexene formation. But now it's a cyclohexadiene product. Why is there an alkene here now? Well, it's because we just use one pi bond here of the alkyne. So the versatility of the Diels-Alder, this is a very useful product, highly functionalized from that alkyne thing. How about this one, where we've got the Diels-Alder reaction happening right here. And what, we're going to form not just one ring, we're going to form two rings. So this is kind of like the cyclopentadiene and the cyclohexadiene, where we can form polycyclic structures. And this is really neat. Let's just, imagine where the Diels-Alder is going to be. It's going to be right here, our cyclohexene. So there it is. Let's draw it. And what goes along for the ride is this other side here. We say that the diene and the dienophile are tethered together. So there's another 1, 2, 4, 5, 6-membered ring formed right over here, okay? And by the endo rule, actually, you can analyze that. I'm not going to take time now. These actually end up cis to each other. As a consequence of this being tucked underneath, you can kind of see if you pull that underneath, this hydrogen will be up, and this hydrogen is also pointing up. So when you do the Diels-Alder right there, it ends up being that product. Again, very versatile reaction. Yeah, I think that's enough of the problems, and we've covered all the, the principles that are on the homework that's due tonight. We've got a couple minutes. Let's go back up here to ChemTube, and I'll show you a couple other examples you can look at for the Diels-Alder reaction. Let's see, Diels-Alder reactions. Let's see if we've got some other ones here. Did the website die there? Oh, no, there we are. Okay, stereochemistry, endo versus exo, Diels-Alder overview. How about quinone? Well, let's see, which one do we want to do? diene. Oh, I think that's the one we just did on the board. Let's see. Yeah, okay. Well, and they're just simplifying the dienophile there. I don't think we want that one. Let's see. How about Let me see if I can find one other good one for you. You can click through these examples and analyze them and, you know, work with your models there. Oh, that's kind of a fun one. Again, it's with an alkyne. You see right there with 2 carboxylic acids there. So pushing around the ring, you can kind of get a feel for that. But what's not readily apparent is the 2 benzenes here, the green phenols that are part of the diene. So you end up being cis to each other. You need to see the transition state for that. And here they've got them oriented. It's in the EE geometry there for the diene. And you see the 2 phenols drawn out there. That's good. And let's see, we can use the controls here and do it back and forth maybe. Yeah, there we go. You can kind of reorient it. Oh, and you see the 2 hydrogens pointing up right there, and there. And the 2 phenyl groups both puckered down, so they're cis to each other. That's a good one there. You can kind of spin it. Let's see. Yep, put it on spin. Well, it lets you see it from different orientations, but you can also drag it with your mouse like I'm doing right now. Anyway, there's a bunch of examples you can click through there. You can access it on any device that you have. It's completely free. It's called ChemTube 3D. You'll get to it if you just enter in your search line there, ChemTube, okay? It'll take you right to it. And under the organic button, you know, look through the examples and that can help you out. So I think we're good to go for chapter 16. Chapter 17 coming up next here on Friday, aromaticity, and stay tuned for that. Very good. We'll see you next time. Thank you.